Okay, let's talk in a little bit more depth about routing protocols specifically. We talked about routing, what it is, how more or less how it works. Let's get into the weeds a little bit. So, if you remember from the routing video, we have the routing table, and every router has its own routing table, and what that contains is basically a list of networks and paths or methods to get to those networks. So in this case, you've got a fairly simple network, really only one route for any device to connect to any other network. Some of them are directly connected, some of them you have to go through one or two or even three routers to get to farther networks away. And that's the metric that's on the right-hand side of each of those routing tables. Tells you how far, how many hops you have to go through to get there. What the router needs in that routing table is the network address, an interface, basically telling the router, which way do I go? How do I connect to this network that I'm trying to get to? And that's stored there in terms of an interface, in terms of the next hop, basically, along that path. And then a metric. And what the metric tells the router is how far that is. And the metric allows the router to compare different routes. So if you had more of a mesh network where there were multiple paths to get from one router to another, in order to know which path to take, what's the best path to take, we keep track of this metric. And the metric allows us to compare different paths to take the best or the fastest path. One way that you could set up those routing tables is called static routing. In static routing, each route is entered manually. Each time your network changes, you have to enter those routes manually. And the metrics or the costs are entered manually. It's fine. Static routing or manually configured routing is fine if you have a small network that doesn't change very often. Basically, once you get past a couple routers, though, you really don't want to be doing this, because then anytime anything changes inside your network, you have to go in and manually update the configuration of the router. And there's just better ways. There's better ways to do it. Really, the cost of static routing is in terms of time and tears for your network admins who have to log in and change those configurations every time anything changes. A great, fantastic old quote that I just made up. Teach a router to route, and it will route for a day. Teach a router to talk to others, and it will route for a lifetime. We've come up with better ways than this static routing, where you have to log into the router and teach it every route and every path that it needs to take. There's better ways. There's better options. Those options are dynamic routing protocols. And there's a few of them. We'll talk about a couple different classes of dynamic routing protocols. But for the most part, what you need to understand is that dynamic routing protocols allow routers to share information between each other. It allows routers to talk to each other to share those routes and to share that information. Now, instead of time and tears of your network admins, this is going to cost bandwidth and router power, right? Your routers are talking to each other. That's taking up bandwidth on your network. Typically, it's not a significant portion of the bandwidth on your network, but it can be if you don't set things up right, or if things change, it can flood your network for a little bit. But what it does allow you to save is that time and tears. And we've talked about it before. People are expensive. People are a very expensive part of networking. And if you can save your network admins time that they don't have to spend configuring routers, then you're going to be much, much better off in the long run. So one class of dynamic routing protocols, dynamic routing protocols are distance vector protocols. And RIP, RIPv2, IGRP, these are the major distance vector protocols that can be used. And for the most part, they use a single metric called hops. And a hop is essentially just the number of routers that you have to go through to get from point A to point B. So that routing table that we showed you at the beginning, that was housing basically a distance vector metric where it says, this is how many networks or routers I have to go through to get to my destination network. If I want to go to the network that's all the way on the other side, I have to go through 3 routers. My metric is 3. And that's going to be the metric that's stored in these distance vector protocols. For the most part, RIP and RIPv2, the way they work is by broadcasting that entire routing table onto the network. So anytime or at a regular interval. So every 30 seconds, they're going to blast out their routing table so everybody knows. And through that, all of the devices on the network eventually learn about all the other networks, because when I learn about another network because another router shared it with me, then I'm going to add that to my routing table. And then the next time I broadcast, that new network is going to be in my routing table that I've broadcast out. So it takes a little bit when you set up a network for this, all of the information to be shared, or when you add a new network, it takes a little bit for all of that information to propagate. But eventually you've got as long as your network's not changing like crazy, you've got a fairly stable routing table inside of each of your routers that's automatically configured. Then when things change, it's automatically shared and those changes propagate through the network, and you don't have to, again, spend that time and energy and tears of your network admins to do that. The other major kind of dynamic routing protocols are called Linkstate protocols. And the Linkstate protocols, like OSPF, Open Shortest Path First, or ISIS, note, it's not ISIS, it's not a terrorist organization, it is ISIS, and that is how it is pronounced. At least that's how Wikipedia says it. Now, the way Linkstate protocols work is, rather than just blasting out that routing table with those metrics in it, they work by creating a map of the network. And they can include a bunch of different metrics. Most commonly, you're going to be using speed as your metric rather than hops. And we'll talk about why that is in just a minute. But you're going to be using speed as the metric inside of your network. And you're going to create the best path. You're going to determine the best path by looking at this map and figuring out what the best way is for me to get from point A to point B. And the great thing about Linkstate protocols, and the reason they've kind of taken over the world, is they only flood the network. They only share anything across the network when something changes. So remember the Distancevector protocols, for the most part, they're blasting out that routing table every 30 seconds, whether anything's changed or not. When something changes on a router in a Linkstate protocol, say if a link goes down or if a new link is added, then that router is going to share that with the network, and it'll propagate out like everything else. But otherwise, it's not going to share anything, and nothing changes, and the network all stays nice and quiet. So much lower bandwidth requirements in terms of network traffic, as long as things aren't changing. So the reason speed matters, as opposed to thinking of hops, the way that a Distancevector protocol might. If we look at the router on the left, the bottom left, and the router on the bottom right, if router A on the left wants to send a message to router B on the right, the shortest way in terms of hops is to send it directly. Now, if this is a small network or a small message, then 10 megabits per second might be plenty, and we can send that across there just fine. But if I want to send a movie, or a large file, a large transmission from router A on the left to router B on the right, the best way is not going to be the one with the shortest number of hops. The best way is the fastest way, and that's taking into account that the up and over route, rather than the direct route, has a significantly faster links all the way across, and we could only do that if we had that map. Because if I have 1,000 megabits to the router up above me and 10 megabits to the router across, well, that's fine. But if I don't know the next step, what about the router up above me? What if it only has 10 megabits to the next hop? Then I'm no better off going that way than I am just sending it directly. So you have to have that entire map of the network rather than just knowing about the connections that you're directly connected to. So we've already I've alluded to this a little bit. When routers start up in any of these dynamic routing protocols, all they know about is what they're directly connected to. And you configure the router. You still have to configure the router to some extent. You have to tell it what networks it's directly connected to, what addresses it has. But then once it's in the network, it's going to start sharing that information. And the router on the left is going to tell the router next to it, hey, I've got 10.16 or 172.16.10. And then the second router over is going to say, hey, network next to me, I've got 172.16.10. So if you need to get there, let me know. I've got it. And that information is shared and gets added to the routing table until we reach what's called convergence. And convergence is essentially that stable state of the network where every router knows the paths and everything about the network that they need to know. And that's convergence, and that's the final state. And all of the dynamic routing protocols are designed to get you to that state of convergence where everybody knows, and whether that's just having these routing tables with the hops or whether that's having that entire map, like in the Linkstate protocols, that's all part of the reasoning there. So there's one other dynamic routing protocol that's very, very important, and it's the border gateway protocol. And the border gateway protocol is what's used at the internet level. So open shortest path first, or RIP, or ISIS, those are great for use inside of a smaller network, or set up a smaller inter-network or an intra-network. But when we're dealing with the scale of the internet, and you think about how many different networks there are that are connected, Amazon's probably got 1,000, and Google's probably got, who knows, tons. There are so many different networks that need to be connected, and sharing all of that routing information would basically require it would require a lot of storage and a lot of packets. And anytime, if we were to use a protocol like open shortest path first, anytime anyone or any network was added to the internet anywhere, the entire internet would be flooded with packets, and everybody's telling each other how to get there and all that stuff. So that kind of protocol doesn't scale well to the scale we need at the internet level, and that's what the border gateway protocol is for. And the way it works is it has this concept called an autonomous system. And typically what your autonomous system is going to be your ISP. Your ISP is your autonomous system, and they have lots of routers and all that other stuff, and they have open shortest path first or whatever protocols running within their network. But then at the border gateway protocol, at that border between their little network and the world, the internet, the big routers that really connect ISPs, for example, at that huge level, we use that border gateway protocol. And the biggest thing that makes the border gateway protocol work is called route aggregation. And the way route aggregation works, typically in your routing table, you've got your subnet, right? You've got a network, address, and you tell people how to get there. Well, the way route aggregation works is it lets you slam together a whole bunch of networks into a single advertisement. So instead of saying, like here in this example, I have 126.159.0/24, which means all of the addresses that start with 126.159.0, all the way through 126.159.255. So I have all of the 126.159 networks, but that's divided into 256 different network IDs that each have their own stuff and they're all doing their own thing. Well, what I can do is I can aggregate those together and advertise just 126.159/16. And that saves us from having those 256 different subnets stored as individual links or individual entries in a routing table. We can have all of 126.159, and that big router at the border says, I have 126.159. If you have anything for 126.159, send it to me and I'll get it there. And that is assigned to an autonomous system. And that saves so much storage space on all of these routers around the world from having to store each individual network. And the more you can aggregate, the better off we are. The more you can aggregate that and advertise more networks as one entry, the better off we are in terms of having to share that information and store that information on how to get there. And so then if I'm on Cox and they advertise 126.159, then anybody in the world who needs 126.159 knows that they just have to get it to the Cox router, and then the Cox router will hand it from there, the Cox border router. And so that's great. And the border gateway protocol, if you're working inside of a local network, if you're not working at an ISP, you're probably never going to be using the border gateway protocol. But it's an important thing to know because that really is how it's the protocol that makes the internet work. We've got our protocols that make connections between networks work, those local routing protocols, but the border gateway protocol is the big protocol that makes the internet routing and dynamic routing possible at the internet level, and none of those other protocols can handle that. And that is routing protocols. And that's routing protocols.